The future of energy is changing, and China is leading the way with its groundbreaking artificial sun project. This revolutionary nuclear fusion reactor has the potential to provide limitless clean energy, transforming the way we power our world. Scientists are working tirelessly to push the limits of technology, breaking records and setting new milestones. As the world searches for sustainable solutions, China's artificial sun is proving to be a game-changer. But how does this futuristic technology work? What secrets lie behind its incredible achievements? And what does it mean for the future of global energy? Today, we will uncover the record-breaking secrets of China's artificial sun and explore the science behind this ambitious project. From its massive energy potential to its role in climate change solutions, this technology is shaping the future. The breakthroughs being made today could redefine how humanity powers its cities, industries, and even space missions. The world is watching closely as China takes bold steps toward a future where fusion energy could replace fossil fuels. Will this technology live up to its promise? What challenges must be overcome before fusion becomes a reality? Join us as we dive deep into the incredible journey of China's artificial sun. Like and subscribe for more insights into the world's most exciting technological advancements. 1. Understanding China's artificial sun. How does it work? China's artificial sun, also known as the Experimental Advanced Superconducting Tokamak, EAST, is a nuclear fusion reactor designed to mimic the energy-producing process of the real sun. Unlike nuclear fission, which splits atoms to release energy, fusion works by combining hydrogen atoms under extreme heat and pressure. This process generates enormous amounts of energy with minimal environmental impact. Inside the EAST reactor, temperatures can reach over 150 million degrees Celsius, making it 5 times hotter than the core of the sun. These extreme conditions allow scientists to create and sustain plasma, the key ingredient in nuclear fusion. The goal is to achieve a self-sustaining reaction, where the energy produced by fusion keeps the process going indefinitely. This breakthrough could revolutionize the way the world generates power, providing nearly unlimited energy with no carbon emissions. However, maintaining these conditions for extended periods is a major challenge. Scientists are continuously improving the reactor's design, testing new materials, and advancing magnetic confinement techniques. Every breakthrough brings us closer to harnessing the power of the stars on Earth. 2. Breaking records. The achievements of China's artificial sun. China's artificial sun has made headlines for repeatedly breaking fusion energy records. In 2021, EAST sustained a temperature of 120 million degrees Celsius for 101 seconds, an unprecedented milestone in fusion research. This achievement was followed by another record in 2022, where the reactor maintained 70 million degrees Celsius for over 1,000 seconds. These breakthroughs demonstrate the rapid progress being made in nuclear fusion technology. Sustaining high temperatures for extended periods is critical for making fusion a viable energy source. Each record brings scientists closer to achieving ignition, the point where fusion becomes self-sustaining and produces more energy than it consumes. Competing fusion projects worldwide, such as the International Thermonuclear Experimental Reactor, ITER, in France, are closely monitoring China's advancements. The success of EAST is a testament to China's commitment to leading the global fusion race. As new techniques and materials are developed, future experiments are expected to push the limits even further. If these advancements continue, we may see practical fusion energy within our lifetimes. 3. The role of superconducting magnets in fusion energy. One of the key technologies enabling China's artificial sun to function is superconducting magnets. These powerful magnets are essential for containing and controlling the superheated plasma inside the reactor. The fusion process requires hydrogen atoms to be compressed and heated to extreme temperatures, forming a plasma that must be confined without touching the reactor walls. Traditional materials cannot withstand such high temperatures, so strong magnetic fields are used to keep the plasma suspended in place. China's EAST reactor uses advanced superconducting magnets, which generate ultra-strong fields while consuming minimal energy. These magnets are cooled to near absolute zero using liquid helium, allowing them to operate with almost no electrical resistance. The development of high-temperature superconductors has significantly improved the efficiency and stability of fusion reactors. Scientists are continuously refining magnetic confinement techniques to enhance performance and extend the duration of fusion reactions. With each improvement, fusion energy moves closer to becoming a practical and reliable power source. 4. How China's artificial sun could solve the global energy crisis. The world is facing an energy crisis, with growing demand and dwindling fossil fuel reserves. China's artificial sun offers a potential solution by providing a nearly unlimited source of clean energy. Unlike traditional power plants that rely on coal, oil, or gas, fusion reactors produce energy without greenhouse gas emissions. This could drastically reduce carbon footprints and combat climate change. Additionally, fusion fuel, hydrogen isotopes such as deuterium and tritium, is abundant and can be extracted from seawater. If successful, fusion energy could replace fossil fuels, eliminating energy shortages and stabilizing global energy prices. Countries around the world are investing heavily in fusion research, hoping to commercialize this technology within the next few decades. While challenges remain, such as scaling up reactors and reducing costs, China's rapid progress has given scientists hope that fusion could become a reality sooner than expected. 5. Challenges in making fusion energy a reality. Extreme temperatures required for fusion reactions, which are hotter than the core of the sun. Containing this superheated plasma requires advanced magnetic confinement systems, such as tokamaks, which are complex and costly to develop. Maintaining stability in these reactors is another major hurdle, as plasma is highly unstable and difficult to control. The development of materials that can withstand intense radiation and heat over long periods is still an ongoing challenge. Current fusion experiments consume more energy than they produce, making net energy gain a critical milestone yet to be achieved. Funding and political support for fusion research are often inconsistent, leading to delays in progress and limited resources. Private companies and governments are investing in fusion, but commercialization is still decades away. Scaling up fusion technology for widespread use presents engineering and logistical difficulties. Developing efficient and affordable fusion power plants requires breakthroughs in superconducting magnets and energy conversion systems. The cost of building and maintaining fusion reactors remains prohibitively high, slowing down potential adoption. 6. Global competition. How China compares to other fusion projects. Fusion energy is the next frontier in clean power, and countries worldwide are racing to achieve it first. China has emerged as a major player in this competition, investing heavily in advanced fusion technology and reactor development. The country's experimental advanced superconducting Tokamak East has set records for plasma temperature and stability, demonstrating China's growing expertise. Meanwhile, international projects like the ITER reactor in France, a collaboration of 35 nations, are working toward large-scale fusion energy breakthroughs. The United States is also pushing forward with private sector investments in startups like Helion and Commonwealth Fusion Systems. Europe has multiple fusion initiatives, including the UK's STEP program, which aims to build a commercial fusion plant by 2040. Russia, a pioneer in tokamak technology, continues to develop new reactor designs with a focus on magnetic confinement. Japan's JT60 SAW reactor is part of a partnership with Europe and is expected to advance fusion research significantly. South Korea's KSTAR reactor has achieved long-duration plasma confinement, proving the country's strong position in fusion development. China's aggressive fusion strategy includes plans for a next-generation reactor capable of producing net energy gain within the next decade. While China leads in experimental progress, Western nations and private companies focus on commercializing fusion power more rapidly. The global competition is driving innovation, with different approaches like laser-driven fusion being explored in the US and Europe. China's government-backed projects benefit from stable funding. 7. The future of fusion energy. When will it become reality? Fusion energy has long been seen as the ultimate solution for clean, limitless power, but the big question remains: when will it become reality? Scientists have been working for decades to achieve sustained fusion, yet no reactor has produced more energy than it consumes. Major projects like ITER in France are making progress, but commercial fusion is still years away. China's East Reactor, the U.S. National Ignition Facility, and private companies like Helion are pushing boundaries, but challenges remain. The extreme heat required for fusion, over 100 million degrees Celsius, demands advanced materials and containment systems. Magnetic confinement, used in tokamaks, and laser-driven fusion are two leading approaches, each with advantages and technical difficulties. AI and machine learning are helping optimize plasma control, speeding up research and reactor stability improvements. Governments and private investors are pouring billions into fusion startups, accelerating development like never before. Some companies claim they could achieve net energy gain within a decade, but large-scale deployment will take longer. The first commercial fusion plants are expected in the 2040s, though breakthroughs could speed up this timeline. The transition from experimental reactors to power grids requires innovations in energy extraction and conversion technology. If successful, fusion could replace fossil fuels, providing nearly infinite, carbon-free power for the world. Unlike fission, fusion does not produce long-lived radioactive waste, making it a safer alternative. The race for fusion dominance is heating up, with China, the US, and Europe leading the charge. Global collaboration is crucial, as no single country can solve fusion's technical challenges alone. Public awareness and government support will determine how quickly fusion progresses from labs to power plants. 8. Fusion energy in space exploration. Fusion energy has the potential to revolutionize space exploration, providing spacecraft with limitless, high-efficiency power for deep space missions. Traditional propulsion methods, such as chemical rockets and nuclear fission, have limitations in fuel supply and efficiency. Fusion, on the other hand, could offer a nearly inexhaustible energy source by using hydrogen isotopes found in water or even harvested from space. A fusion-powered spacecraft would be capable of faster and more efficient interplanetary and interstellar travel, reducing travel times significantly. Unlike solar panels, which become less effective in deep space, fusion reactors could provide consistent power regardless of distance from the Sun. This would enable permanent lunar bases, Mars colonies, and missions to the outer planets without the need for frequent fuel resupply. Developing compact and efficient fusion reactors for space travel remains a challenge, as current designs are large and complex. Magnetic confinement fusion, used in tokamaks, and laser-driven fusion are both being explored for space applications. The extreme conditions of space, including microgravity and radiation, add additional engineering challenges to fusion reactor designs. Scientists are also considering fusion-based propulsion systems, such as direct fusion drives, which could cut travel times to Mars from months to mere weeks. If successful, fusion propulsion could make human exploration of Jupiter's moons, Saturn's rings, and even interstellar travel a possibility within our lifetime. NASA, private companies, and international space agencies are investing in fusion research with the goal of making it space-ready. Advances in superconducting magnets, AI-driven plasma control, and energy conversion systems are bringing fusion propulsion closer to reality. Mining helium-3 from the Moon has been proposed as a potential fuel source for space-based fusion reactors. A successful fusion spacecraft could enable robotic probes to explore exoplanets far beyond our solar system. Unlike nuclear fission, fusion does not produce harmful radiation that would endanger astronauts or spacecraft electronics. 9. The environmental benefits of fusion power. Fusion power has the potential to revolutionize energy production while offering significant environmental benefits. Unlike fossil fuels, fusion does not produce greenhouse gas emissions, making it a truly carbon-free energy source. By replacing coal, oil, and gas, fusion could help combat climate change and reduce global air pollution. Unlike nuclear fission, which generates long-lived radioactive waste, fusion produces minimal and short-lived radioactive byproducts. The primary fuel for fusion, hydrogen isotopes like deuterium and tritium, can be extracted from water, ensuring a nearly limitless and sustainable fuel supply. Fusion does not require uranium or plutonium, reducing the risks associated with nuclear proliferation and radioactive contamination. A successful transition to fusion energy could dramatically reduce humanity's dependence on environmentally harmful energy sources. Large-scale fusion power plants would not require massive land areas like wind or solar farms, minimizing ecological disruption. Unlike hydroelectric dams, fusion does not affect river ecosystems or displace wildlife habitats. Fusion reactors produce no combustion byproducts, eliminating harmful pollutants like sulfur dioxide and nitrogen oxides that contribute to acid rain. Unlike fossil fuel power plants, fusion facilities do not require extensive mining, drilling, or fracking operations, preserving natural landscapes. The waste produced in fusion reactions consists mainly of helium, an inert and harmless gas that does not contribute to atmospheric pollution. Advances in fusion technology could enable decentralized energy production, reducing the need for long-distance power transmission and minimizing grid losses. Fusion energy could provide stable, 24/7 power generation, unlike wind and solar, which depend on weather conditions. The adoption of fusion could lead to a decline in deforestation, as fewer trees would be cut down for biomass or land clearing for energy projects. If implemented globally, fusion energy could significantly reduce water consumption in power generation, as it requires less cooling water than traditional nuclear and coal plants. Countries that rely on fossil fuel exports would need to shift toward more sustainable economic models, fostering a greener global economy. Fusion-powered desalination plants could provide clean drinking water without the high energy costs and environmental impact of current methods. The environmental benefits of fusion could support global efforts to achieve carbon neutrality and create a cleaner, healthier planet for future generations. Though challenges remain in making fusion a reality, its potential to transform energy while protecting the environment is undeniable. 10. The final breakthrough. What's next for China's artificial sun? China's Artificial Sun Project, the experimental advanced superconducting Tokamak, East, has been making headlines with record-breaking plasma temperatures and sustained fusion reactions. The project aims to replicate the nuclear fusion process of the Sun, creating a nearly limitless source of clean energy. East has already achieved temperatures of over 150 million degrees Celsius, nearly 10 times hotter than the Sun's core. The challenge now is to sustain these extreme conditions long enough to generate more energy than the reactor consumes. Scientists are working to improve plasma stability, enhance magnetic confinement, and extend reaction times for continuous power generation. East is a crucial stepping stone for China's next major fusion project, the China Fusion Engineering Test Reactor, CFETR, which aims to bridge the gap between experimental research and commercial power plants. CFETR is expected to be operational by the 2030s, with the goal of producing steady-state fusion power. The success of China's artificial sun could give the country a leading role in the global race for commercial fusion energy. Unlike fossil fuels, fusion power produces no carbon emissions, making it a critical technology for China's clean energy transition. Advances in materials science, AI-driven plasma control, and superconducting magnets are accelerating fusion research. The integration of machine learning is helping predict and stabilize plasma behavior, reducing disruptions in the reactor. China's fusion research is closely linked to international efforts, including its participation in the ITER project in France. While East and CFETR are government-funded, private investment in fusion technology is also growing in China. If breakthroughs continue at this pace, the future of fusion energy is closer than ever. Will China lead the way in the next energy revolution? Like and subscribe for more insights into the world's most groundbreaking innovations.